Hello and Assalamualaikum. We are from group Agugerl, which consists of 5 team members, which is the first one, me myself, Shaquirra R, Lerado, and we have Hazura binti Harun, Nuralya Sabrina, Ainul Jazmina, and lastly Fatin Nurhaziqah. Today I'll be presenting our project on the beam engine mechanism, which is designed for cutting applications. This mechanism is inspired by traditional steam engines, where an overhead beam creates a reciprocating motion. We have adapted this concept into a complex system that uses a motorized disc, rod, and a beam to drive a mini hacksaw blade back and forth. This is how it works. The motor rotates a disc connected to a rod, and then this rod will pushes and pull the overhead beam, and the beam then drives the hacksaw blade, producing a precise reciprocating motion. A small workbench is added to hold materials such as plastic, wood, or thin metal sheets during the cutting. The main goal of our project is to study the kinematics, force transmission, and efficiency of this mechanism. We also explore how motion is converted and transferred through different linkages. As part of the project, we have developed a CAD design, run kinematic simulations, and perform a basic analytical analysis. Overall, this project helped us apply mechanical theory to a real-world machine, improving our understanding of motion system and mechanical design.
For our design selection, we are choosing the mini hacksaw powered by beam engine. The reason we are choosing this design because the first one is educational value and simplicity, because this design is ideal for learning mechanical linkage and motion conversion like rotary to reciprocating. And the second one, because of cost effective, this design is utilized affordable and widely available materials, making it budget friendly for educational project. And the third one is compact and practical. This mini hacksaw is in small size and easy to set up in limited spaces, perfect for hands-on learning. And the fourth is because of motion control and efficiency. This mini hacksaw provides smooth, controlled, reciprocating motion. And the next one, because of analytical feasibility. This design is easily analyzed with basic calculation and simulation. And the last one, because of a unique mechanical insight. The mini hacksaw powered by the engine is a great example for historical mechanical principle in modern technology.
So in this slide, I'm going to talk about the assembled AutoCAD design of a mini hacksaw powered by a beam engine. The design converts a rotary motion into a back and forth cutting action. Key parts like the beam, crankshaft, and the hacksaw blade will work together to ensure smooth operation. So there are 3 different views which to help visualize the structure as well as how the components fit together, which is firstly the top view. So the top view shows how the components are arranged from above. So we can see the overall layout, including the beam, the crankshaft, as well as the hacksaw frame. Second view is the front view. So this view gives a direct look at the machine's height as well as how the components are stacked together. So we can clearly see the beam's movement and the saw blade's cutting path, as well as the frame supporting the system. So last view is the side view, and this view provides insight into the depth and the profile of the design. So it helps visualize the motion of the beam and how power is transferred from the crankshaft to the saw blade.
Hi, I'm Fatin. I will explain about velocity analysis and displacement diagram by using SL analysis. So for velocity analysis, all lengths are given for AB, BC, CD and AD. And for angle at BCD, we assume it as 60 degree. The scale is 10 cm to 2 cm. So from the information given, we can get VBA, which is 2.65 meter per second. And after we have done the velocity analysis, we will get the velocity triangle. By measuring it, we will get VCD and VCB. Also, we will get angular velocity for CD and CB. To conclude, the velocity analysis provide critical information about the motion of points within the linkage. Also, the calculated angular velocities confirm direction and magnitude of the motion. For displacement diagram, you can treat it as 4-bar linkage that shows how the positions of the links change as the crank rotates to 360 degree. It helps visualize and analyze the motion. This diagram represents the crank angle for x-axis versus the link displacements for y-axis. It shows the periodic motion of coupler and output links. For key observations, for periodicity, the motion repeats for every crank rotation, while for the amplitude, it peaks show the maximum or minimum displacement. And lastly, for the synchronization, the intersection indicate key system positions. This diagram ensures the linkage design meets functional requirements like synchronization and efficiency. It's vital for analyzing and optimizing motion.
Now I will presenting the kinematic analysis simulated using ANSYS software resulted as shown here. From the simulation, we observe a maximum angular velocity of 645.71 radian per second and peak angular acceleration of 2.32 times 10 power of 8 radian per second square on the saw blade. This large fluctuation suggests highly dynamic motion which may affect cutting stability and blade durability. Meanwhile, the motor shows steady acceleration indicating a reliable power input. When we compare to theoretical value, the results mostly align, but the high acceleration spikes suggest a need for smoother transition. Therefore, we propose modifying the linkage geometry or adding a flywheel to reduce motion shocks and reinforcing stress-prone area to improve structural integrity. We can see by the simulation, it offers valuable insight for improving efficiency, durability, and performance of the Hacksaw mechanism.